Hello, everyone. Can you hear me?
Hello, how are you? Oh, I thought I unmuted.
Hey, Jeff.
Yeah, okay.
Good to see you. Hey, John.
Hi, Jin.
Hey.
Hello, everyone. Good afternoon, and welcome to the technical session number 3. I'm Yi Qi. I'm the faculty from Texas Southern University. I will be served as a moderator for today's session. And the topic for this session is improving multimodal mobility, leveraging data and advanced analytics. So we have 4 speakers for today's session. And our first speaker is John Ivan, a professor at the University of Connecticut. His topic will be estimation of pedestrian volume using geospatial and traffic conflict data. So John, you can share your screen and get...
No, I can't because it's disabled at the moment.
Okay, so the meeting host, please give this privilege to John, let him to share the screen. Hey, Penfei?
Yeah, Mr. Yuan, you can share your screen now.
All right, I did not get a notification, but there we go. Yes, it's working now.
Okay, good.
All right, let me look for... okay, there it is. Whoops, I was at the very, I forgot I was reviewing and I had it at the end of the presentation. Sorry about that. Okay, so thank you for the introduction. I'm very happy to talk about some of the research that I've been doing on project 12 from last year. Called Estimation of Pedestrian Volume Using Geospatial and Traffic Conflict Data. I want to acknowledge my co-PI, Amy Bernicki from the Department of Geography here at UConn. I'm in the Department of Civil and Environmental Engineering. And also my graduate student, Pankaj Joshi, who did most of the, really did the work here that I'm going to be talking about. So I'll just go ahead and start. So the project is, we motivated our wanting to do this research was we're recognizing that increasing walking and use of public transportation, which requires walking for part of the trip, is an important objective in reducing greenhouse gas emissions and making cities more livable. But at the same time, NHTSA data, that's National Highway Traffic Safety Administration, has shown that pedestrian fatalities have been increasing in recent years, even as the total road fatalities have decreased. So even though you might see in the news that the roads appear to be getting safer because the total fatalities on the highways have been dropping, in fact, the number of pedestrian fatalities has not been decreasing and in fact has been increasing, and certainly been increasing as a percentage of total fatalities. So that really works against the idea of improving or increasing people walking. And strategies to promote walking, so then if we're doing some stuff to try to improve walking, it's not likely to be effective if people don't feel safe. So building the transit-oriented development and walkable neighborhoods, if people don't feel safe walking, then that's not likely to be effective. And also, one of the ways we're thinking to represent how safe people might feel would be a quantitative measure such as conflicts between pedestrians and motor vehicles. So if when people are walking, there's a high proportion of the time they're walking, they end up in a close encounter with a motor vehicle, then that might really discourage them from walking. Or if they see that as then with someone else experiencing that, then that might discourage walking. So the idea of this project is that we want to incorporate a measure of this perceived safety, which we're defining as the ratio of severe conflicts between pedestrians and motor vehicles to the number of less severe interactions. And so we're going to incorporate this into models predicting pedestrian volume at intersection crossings. So the objective here is to test the hypothesis that a higher ratio of conflicts to interactions is associated with a lower total pedestrian volume. So the idea here is not so much to use this for predicting the total volume, but we're just using this in a model to see if that's significant for explaining how many people are walking. So talking about the data first. So we collected, or rather we acquired the pedestrian crossing and vehicle interaction data from the archives of 3 projects that I was involved with in recent years that were funded by other UTCs, where we observed interactions between pedestrians and motor vehicles, which included conflicts and lower level interactions as well. So those data were already there, and we didn't have to collect them again for this project, and that was handy. But what we did for this project was acquire additional GIS land use and coverage data, because we didn't have that for the previous projects. So what we're doing now is we had data that described the crosswalk and the street where the pedestrians crossed, but we wanted to get information about the land use surrounding each area, where each crosswalk where the observations were made. And at this point for the project, what we have is data covering 3 towns in Connecticut: Ansonia, Hartford, and Waterbury. And I'll say a little bit more about that towards the end. But for now, we have these three towns. So the specific data that we gathered, so from the previous projects, we have the pedestrian volume and the vehicle interaction data. So specifically at these locations over about 6 hours, we would observe pedestrians crossing the street. And then we would classify the pedestrian crossing into one of 4 different vehicle interactions, which were, at the lower end, we had what was called undisturbed crossings, which means the pedestrian crossed the street and there was no other vehicle around, or if there was a traffic signal, all the vehicles were stopped. And so therefore there was no concern about being hit by a car. Potential conflicts means there was a natural interaction between the pedestrian and the vehicle, but there was really no chance of a crash, of the pedestrian being hit. Basically, the vehicle was already slowing down, and so the pedestrian crossed the street as the vehicle was already clear it was going to stop, or the pedestrian waited before the car went by, or the cars, like I said, the car stopped for the pedestrian. So it was something like that. There was an interaction, but there wasn't really any possibility of a crash. And then the minor conflicts and serious conflicts is the other category. And that meant that the pedestrian and the vehicle were on some sort of a collision course. The difference between minor and serious being just how many seconds it was before the possible collision occurred, and also how fast the vehicle was going, and which would indicate a serious conflict would have indicated it would have been a very serious crash, and a minor conflict would have been maybe a less severe injury for the pedestrian. So we classified them into those 2 categories. And then the new data we collected were the geospatial and street network data. So we got the link to node ratio and the average block length, which were calculated from the maps that were acquired, geographic maps that were acquired for those areas. And then we built 1/8, 1/4, and 1/2 mile buffers around each intersection, which are not line of sight. They were distances along the street network where people could be walking. So the idea was what's within 1/8 of a mile, what's 1/4 of a mile, and 1/2 of a mile walking distance from that intersection. And then what we did was we got the land use data covering every parcel inside each buffer. So we collected that from town records where they had parcel data available, and we knew what the land use was in each of those parcels. So for every parcel within each of these buffers, we collected the land use data for that, as well as the size of the parcel. So here's some specific statistics for the variables we collected. We collected both the area for each of these land use types as well as the count, which would be the number of parcels inside the buffer. And this gives you the variables just for the 1/2 mile buffer as an example. We have similar statistics for the 1/4 mile and the 1/8 mile buffers. So we have residential as one type of land use, major commercial, which would be larger, larger shops and offices, industrial. We had offices, and then very minor commercial, which would be smaller shops. Institutional, which would be things like government buildings and maybe churches. Parking, which would be literally just a parking lot or a parking garage. And then parks and recreation, which would be more open space, and that would be some public spaces that are in the area. So again, we had both the area and the count for these. So for residential, we expected that the count might be more important because having a large square area of residential is not the same, does not tell you the whole story, because the homes could be very densely placed there, or they could be sparsely placed. And I think the density of the homes was a more important variable there. And the same could be true for some of these other variables. So we tried representing them both ways. And then average block length was there as well. Notice that we mentioned another street network variable. That one was not significant. So this is the one that we used. So the model form we used was a log linear. So what we found was that the P sub I, which is the observed pedestrian crossing volume, the log of that, this graph here shows you a histogram of the log of the total pedestrians crossing at each crosswalk. We found that it was passing a chi-square test to be represented by a normal distribution. So we used the log normal or a regression. So the main variable X there is the conflict ratio, which we defined as the odds of a highly severe conflict or conflict to the ratio of that to the undisturbed and potential conflicts. So we have the numerator was the number of minor and severe conflicts at the location. That was divided by the total of the undisturbed and potential conflicts. So that's the conflict ratio we used. Then the W is the geospatial variables of that location. And then, so then we have these parameters, these linear parameters, alpha, gamma, and beta that were estimated. And then of course we have the random disturbance for the normal distribution. So we looked at a number of different models, but this is the final model that we selected for these three towns. All these variables are significant. The non-significant variables we dropped out and just kept and worked with this final model. So what you'll see is that, so we have the conflict ratio as the first variable there, and it is significant with a negative sign, which is what we anticipated. And so it indicates that indeed the number as the ratio of conflicts to non-conflicts, or severe interactions to non-severe interactions between vehicles and pedestrians increases, then the number of people walking is significantly lower. So it's very significant for explaining the amount of walking. We included those other variables only just to control for that, because we expect that those are all going to be important for explaining the amount of walking. So we just included them just to account for essentially how much walking there should be based on what's going on nearby. So again, the point is not really about those, but those are all showing up about the way we would expect. And I'll talk about that next in the next slide. So the R squared and the F statistic are all very reasonable for showing that we have a decent fit for the data. So as I mentioned, several of the land use intensity variables were significant. So major commercial and office and minor commercial uses, those increased the PED volume. When there's a lot of that increased the amount of pedestrians, which is expected because those are the kinds of things that might be generating people walking in and out of the businesses. Industrial uses and parking uses, those were decreasing the volume. And industrial, because people generally don't walk to a warehouse or a factory or something like that, so that's not surprising. And the parking also, I mean, obviously people may park, they might walk after they go to the parking lot, but if there's a lot of parking, then you're also probably having parking right on the site, and so then people aren't walking actually on the street, they're just walking into the location, and they wouldn't necessarily be walking over to this particular crosswalk. And as the average as the average block length increases, the pedestrian volume decreases as well. That makes sense because it becomes less walkable. That's one of the hallmarks of a walkable neighborhood, is having a short average block length. The high block lengths result in longer distances to walk, so that would decrease the walking. And of course, the main variable we wanted to look at was the conflict ratio. As the conflict ratio increases, the pedestrian volume decreases, and quantitatively, the way we can show this is a 1% increase in the conflict ratio results in a 5% decrease in the pedestrian volume. So that's fairly significant. So in conclusion, we found that the pedestrian volume at crosswalks is significantly negatively correlated with the observed ratio of pedestrian vehicle conflicts to less severe interactions. So this suggests that if we want to improve use of walking as a travel mode at a given location, it would be helpful to reduce the incidence of conflicts. So essentially, countermeasures such as installing better control measures or making the crosswalks more effective, particularly more visual, more noticeable to drivers. These are the things that might help to reduce the conflict, so that drivers are expecting there to be pedestrians and there would not be as much of a, and you might just reduce the, you might make the interactions between vehicles and pedestrians go a bit less severe, become less severe. You can also reduce conflicts through placemaking design. So like extension of curbs that increase the pedestrian space and reduce crossing distance. That would reduce the exposure of pedestrians so they're not in the street for as long a distance, and therefore there's not going to be as much of an opportunity for the interactions with vehicles. And also maybe median islands to reduce the crossing time, and different other things to reduce the visual width perceived by motorists, so that motorists are driving slower, and that would also reduce the likelihood of the conflicts. One thing I also want to note is that again, this was just 3 towns in Connecticut. What happened as we started the project is we discovered that the parcel data that we wanted to use were not as available for all towns as we had expected. So for those 3 towns, they were available readily, and we were able to work on that. But meantime, we spent the summer, we had to do some extra work in actually collecting the data manually from town websites to get the parcel data and transfer that into a GIS. And so we just now have completed compiling all that data, and we're estimating models now with the final data set, and we haven't quite finalized those models yet. So I'm just showing you these preliminary models, but we're finding the same results. The same kind of variables were significant for the geospatial cases, and then also the conflict ratio continues to be significant in a negative, for the negative sign. So we're seeing the same kinds of things for our final results. And I'll be happy to answer any questions unless you want to hold them till the end.
Okay, do we have any questions from the audience? Okay, John, I have a question. Very interesting research. I saw you consider the safety impacts on the pedestrian volume. And did you think the security aspects, for example, the crime rate, so if the location have lots of crime, may also affect the pedestrian volume?
That's a really good point. We did not consider that. We were specifically just looking at the safety, but that's, I suppose some of those statistics might be available. We could conceivably consider that if we can find that easily, we'll add that in. But if it takes a lot of work to compile those geographically, then I don't think that would be possible at this point. I mean, that would maybe another project.
Because I asked questions a few years ago, we did
If somebody's saying something I can't hear, if someone is, the volume is very low.
Okay, can you hear me now? Hello?
No, I can't hear whoever's talking, the volume is very low.
I cannot hear anything. So whoever wants to ask questions, could you please raise your volume or just raise your hand, and we can solve you. Okay, maybe just some background noise.
There we go. I can hear now. Yeah.
Okay, good. So let's move on to a very good presentation. Thank you, John. And let's move on to next speaker. Our next speaker is Jeff Cohen, also a professor from University of Connecticut. Jeff will present his research on the topic of highways and wealth distribution, a geospatial analysis. Okay, Jeff, are you able to share the screen?
Yeah, I need to share my screen. Let's see if it'll work. Are you able to see that?
Yes.
Yes, okay. Well, I'd like to thank everybody in CAMMSE who's made this research possible, including Wei and everybody else on his team at UNC Charlotte. And the CAMMSE team has been really great over the last several months as we've been developing our final report for this project. This project is joint with Professor Nick Lowndes from UConn, who heads up the University of Connecticut's arm of the CAMMSE team. And so this is work that has been going on for quite some time, and you'll see in a minute why it's something that would have gone on for quite some time. Also, I'm a professor in the finance department in the business school. I'm also affiliated with the Connecticut Transportation Institute at UConn, who is administering part of this project. So the idea here is to try to get a handle on the interlinkages between land use patterns and transportation. And specifically, we're looking at the impacts of interstate highways. And we know as cities get bigger and they start to develop more and they become more dense, there's typically, more need for more highways and more ways to get products shipped in and out of the cities. And that leads to more growth. And so you've got this cycle, a continuous cycle, okay? And that impacts property values, and higher property values impact the whether or not people are going to move into the city. And then that leads to a more need for highways as well. So the effects are challenging to sort of try to separate and try to see where the cause and the effect is going on here. And so sometimes this is referred to as the chicken versus the egg problem. Which came first, right? Did the highway come first and then people moved there? Or were people living in a place first and then the highway came there? So one of the things that we're going to try to do is to try to exploit the unique aspect of the interstate highway system in the northeastern part of the United States, which was first announced in the 1940s, right around the time of World War II, and then was constructed and developed in the 50s, 60s, and early 1970s. You may be aware of the fact that after World War II, Eisenhower and the US Allied forces went into Germany, and they saw the sophisticated road and highway national highway network that Germany had. And then the story goes that General Eisenhower then came home and said, we've got to do something like this in the US. And the purpose at that time was to be able to move its military around. But as peacetime progressed, and in the US there was less need for moving military equipment around, it became important for people to travel, transport goods, and so those were the main main uses later on of the interstate highway system, especially in the US. The other aspect that we're going to look at here is, okay, well, you would expect maybe that for some properties, the value of those properties would have gone up after the highway system was built and maybe even announced. And that's due to the fact that there's the benefits of proximity and being able to go places a lot easier. On the other hand, for some properties, you've got noise, you've got congestion, you've got pollution. So for some properties, the impact would be detrimental and cause property values to go down. And so the question is, does this impact different people differently? Do some properties experience disproportionate amounts of the housing wealth gains for those properties that have gone up in value? And do other properties that have gone down in value, possibly due to the noise and congestion, are there some people who experience disproportionate losses due to those effects? And so there have been some people who've taken a look at transportation policy and inequality. The research is a little bit sparse, especially with respect to housing wealth. So that's a central focus of this project. So the research questions that we focus on are, first of all, what are the relationships between proximity to the highway and the value of a house's either appreciation or a depreciation? We use a quasi-experimental identification strategy called difference and differences to try to disentangle the causality here. And that enables us to basically say, okay, we need to look at pre and post highway construction. So we do that for the same properties. And we are able to get a unique data set that we actually had to manually compile from 1940 census data on individual properties. And we matched that to properties that also were still around after the highways were built in the 1960s to see pre versus post the highway. What is the relationship between house values and proximity to the highways for properties that are close versus far from the highway? And then we also look at equity and whether or not the distribution of the wealth that may have been attributable to the highways are equitable or not. And finally, we take a look at the spatial distribution of house value changes. I'm not going to spend a lot of time on the previous literature because there's a lot of other stuff I want to talk about, but there's a big, huge literature on the impacts of highways on productivity of businesses. There is also some work on the real estate impacts, but no known work that looks at the benefits of highways going all the way back to 1940 data before the construction or even the announcement of the highway system. So that's one of our main contributions, and the focus on the real estate impacts together with the much older data set that people haven't looked at all is one of our contributions. So we already talked a little bit about the noise and the congestion issues here. As it would be nice to be able to try to see if we can see in what situations the noise maybe cancels out the benefits of the proximity to the highway. So I already mentioned this is going to be a before and after study. We're going to look at changes in property values before versus after the highway announcement and construction for properties close versus far from the highway. And we're going to focus on Hartford, Connecticut, being, the flagship University of Connecticut is in Connecticut. We're focusing on our local capital, state capital. This is a picture of what the interstate highway system in Connecticut looks like. I don't know if you can see my cursor. I'm moving along here. This is I-84. It starts up in Massachusetts. It goes sort of southwest and it crosses through Hartford, which is right here. That's the state capital. And it continues on all the way to upstate New York, where that goes further out to Pennsylvania. I-84 is going to be the focus of our study here, although as we're going to see, there's a little bit of an impact of I-91, which goes north-south in Connecticut from Massachusetts down to New Haven, which is where Yale University is located. This picture here just shows you, this was compiled by one of our UConn colleagues in the School of Engineering, Norman Garrick, which shows you an aerial photograph of the same area. The left side is before the highway was built, and the right side was after I-84 was built. Okay, so as you can see my cursor moving here, this is I-84. Before it was built, there was a smaller road here, but this big section right here, there was residential housing, a lot of residential housing, as you'll see in a couple of minutes, which some of which disappeared later on, some of which stayed. We're going to see that the properties in this neighborhood right around here, just south of the highway, tended to appreciate the most out of all the properties in the area. Properties that were beyond a half of a mile from the highway. We're going to see that in a few minutes, but this is just intended to give you an idea of why this is an interesting problem, right? You've got You can see the difference in the landscape after versus before the construction of the highway. The other thing we're going to look at is something called the Lorenz curve, which basically tells us how well wealth changes are tracking the number of property owners. So what we have here on the x-axis is the cumulative percentage of houses that were sold in the 1960s, and on the y-axis we have the cumulative change in the percentage change in the wealth among property owners. So what we do is we look separately at properties that went up in value and properties that went down in value. So if you're at the 45-degree line here, this means, for instance, at this point in the middle, this means that 50% of the homeowners experienced 50% of the change in wealth. Okay, so that's an example of an equitable distribution of wealth. If you have a curve that's below the 45-degree line, like this dotted line, then for 50% of the homeowners would have experienced less than 50% of the wealth. So there's a little bit of inequality in this type of a situation. Okay, so we'll see more about what the data show for this situation in a few minutes. Just to talk a little bit more about the data, the 1940 census data is available on microfiche, which basically means you have to have somebody sitting in a location in a public library where these microfiche are available, inputting the data into a spreadsheet. We had someone who spent hundreds of hours doing this, and we were able to obtain information on the property address and the property value for individual properties in Hartford. This person also had to collect matching data from the Hartford's assessor's office. And unlike a lot of more modern assessor's data, that data had to be manually entered because it was on paper. And so she had to sit in the Hartford assessor's office for many, many hours. We were able to match 2,500 properties that were near the highway. It was a very arduous task. We were able to match 2,500 for the 1940 with the 1960, so we could see after versus before. And then after we did that, we geocoded everything along with street maps from 1940 to calculate the distance to I-84, and we created some indicator variables for different cutoffs, like a quarter of a mile, half mile, etc. There's some challenges with trying to include too many distance variables in one regression. I'll talk about that a little later. One of the other things we did was, well, you know, nationwide, as you can see from the period of 1940 to 1960, there was an increase in property values. So we wanted to control for the fact that there's a national rise and increase in property values, and we do that with a real estate price index, basically deflating the 1960 data so that it would be an equivalent $1940. So we're trying to purge the effect of any national level of increase in house prices and try to isolate the effect of the highway itself. So what we have here, this shows us what the real, in $1940 percentage change in house prices was in these neighborhoods. On average, the average house appreciated by about 250%. And some of them went down but the vast majority of them went up in value. A quarter of a mile, only 3% of our sample were within a quarter mile of the highway. When you go all the way out to a mile and a half, you had about 72%. And the average home in 1940 was worth about $6,060. So hopefully that gives you an idea of the data set that we have. And this is when we geocode the properties, this is what they look like in terms of, this is the highway that you saw the picture of before. And we create buffer zones ranging from 0.1 to 0.5 miles. We go further out in the data. We go all the way down to here, which is about 1.5 miles, which will be interesting to see in a few minutes. But let me show you this picture right here. This is the dollar change in house values. This is the percentage change. So when you go to the dollar change, you can see that there's a big area right just south of the highway that is very dark in color, which is greater than $15,000 in appreciation in 1940 dollars. So, further to the north and west, you see some red ones, which is where some of the concentrated falls in property values were. This is our regression results right here. So what we do is we run several different regressions. The dependent variable is the percentage change in house value from 1940 to the 1960s. The main regressors that we focus on are indicator variable for being near versus far. So for instance, nearer than 0.25 miles, we see that the coefficient on the indicator is negative but insignificant. And then when you go out to, so it's likely in this situation that the proximity benefits are being canceled out by the noise and pollution. But as you get to half a mile, you see that the coefficient is 0.47, which implies that if you're within the 0.5 miles, houses were valued at 47% more than other houses, roughly. As you go further out, you see that this indicator decreases all the way out when you get to 1.25 miles, the coefficient becomes 0.19. And then when you get to 1.5 miles, suddenly it increases. And we started scratching our heads as to why that would suddenly happen. You move out, you move away, you go down, and then suddenly it goes up. Well, if you go to this map here, 1.5 miles is like down around here where you're close to I-91, a different highway that we didn't consider in our analysis. This is I-84. This is the one that we were aiming to get at. So even though you're getting further away from 84, when you're down around here, you're getting closer to this other interstate highway. We also include fixed effects for the year, which are basically indicator variables for the years, and the census tracts to control for spatial differences in these properties. Also, we also control for the house value in 1940, and we see that the coefficients are very small but statistically significant and negative. Some of them are around 0.00023 or so, which implies that for every $1,000 higher a house value was in 1940, the change between 40 and 60 was 23% lower on average. So the more valuable houses actually appreciated less after you hold constant proximity to I-84. Here's the wealth distribution analysis for houses that appreciated between 1940 and 1960. So houses that went up in value, there's around 2,000 of them out of the 2,500 or so went up in value. And we see that the curve, the Lorenz curve is the blue curve, the orange curve is the 45-degree line. We see that there's some inequality. For instance, if you're at this point right here, 60% of the population is experiencing only about 40 or 45% of the appreciation in house values. So there is a little bit of inequality here. So that is interesting, but this is really interesting. This is the Lorenz curve for houses that actually went down in value between 1940 and the 1960s. And there were about 60 of those in our sample. So what does this tell us, for instance? So pick this point right here, for instance. This says that about 20% of the households experienced about 80%, or over 80% of the depreciation in value in house prices. So the damages from being close to the highway that may have caused the prices to go down were very unevenly distributed, and possibly you could say inequitably distributed among a very small portion of the homeowners. So that's a fascinating finding that we thought as well. So conclusions and future work that we're thinking about. If you look visually, we see that the spatial distribution showed that greatest appreciation was immediately south of the highway. If you're really close to the highway, there was no price change effect, but there could be benefits from access that were being offset by congestion and noise. As you get further out, the effect the effect is quite large at 0.5 miles, but then it decreases as you go incrementally further out, and then eventually you see a big bump, but that may be from coming closer to a different highway. In terms of wealth distribution, we see some evidence of wealth inequality for houses that increased from 1940 to the 1960s. And we see very dramatic wealth inequality for houses with negative price change in that same time period. Finally, in future work, we would like to, so this was a pilot project in some sense. We would hope that at some point we can take another deep dive. The main restriction is the data, and going back and trying to do that is going to be very time consuming. But we might be interested in looking at other parts of the city and other highways in the city and in the state of Connecticut, and do those elasticity results hold up for the proximity. Looking other parts of the country, big cities versus small cities. Do we see differences in, say, New York City or Los Angeles versus what we saw in the capital of Connecticut? We would love to go back and take a deeper dive with the 1940 census data and try to gather some of the other data that's in there on demographics, including race, income, and gender. And then we would like to explore wealth distribution in more detail. For instance, looking at how does the wealth distribution change for different homeowners of different demographic groups? For instance, do higher income homeowners demonstrate different wealth distribution than lower income homeowners? Or perhaps minority homeowners are bearing more inequality relative to other races of homeowners. So there's a lot we could do in future work. Again, this is a pilot project. Given the complexity of the data, it was a challenge that was the biggest challenge with this project, or one of the biggest challenges was gathering the data that really no one has looked at before from these two time periods. So thank you for listening. I'm probably out of time. Welcome discussion or questions. You're always welcome to email or call me, and thank you very much again.
Okay. Any questions from the audience? Okay, very interesting presentation, Jeff. I really enjoyed it. Thank you. Okay, so our next speaker is Dr. Xianming from Washington State University. So his topic is developing friction data to support the optimal use of pre-wet de-icing silt in Pacific Northwest. Let's welcome.
Right. Thank you, Professor Chi. Can you hear me all right, or see my slides?
Yes.
Okay, so maybe I should get started. So again, thanks for the introduction. And my talk will be on developing friction data to support the optimal use of pre-wet de-icing salt in Pacific Northwest. And this work was mostly done by my colleague, my PhD student, Yan Zhang. And here's the outline of the talk. I'd like to give a little bit introduction or background on why such best practices are needed in winter road maintenance operations, and then talk about the work we focused on Pacific Northwest and one of the best practices, which is called pre-wetting. Essentially, if you look down the picture on the left, that's putting liquid salt brine onto solid salt, so that when you look at the photo in the middle, when the salt is placed on the road, by pre-wetting it, you reduce the bounce and scatter, and there are a number of other benefits, as we'll mention later in the slides. And the ultimate goal is to reduce the amount of salt introduced into the environment so that the environmental risk or damage is minimized. Of course, we're not trying to jeopardize any safety or mobility, but we want to put in as little as possible in terms of introducing salt into the environment. And then we will talk about the results of a lab investigation of pre-wetting, look at how effective or how ineffective they are, and then conclude. So to start with the bigger background, why do we need best practices in winter road maintenance? Well, again, I'm sure this looks familiar. I've presented this one before. So this is a map by Federal Highway Administration looking at the area in the blue dots, basically 70% of the roads and 70% of the population are affected by snow and ice. Typically, the definition is more than 5 inches of snow and ice each winter season. So for highways alone, the US is spending approximately $2.3 billion. And the damage of such operations to transportation infrastructure is estimated at another $5 billion per year. And the environmental cost is really hard to quantify. And typically, in addition to plowing, what agencies do is they put down de-icers, anti-icers, and abrasives. And some of these materials, well, all of these materials eventually will find their way into the vegetation, soil, surface water, and groundwater. And here's one mechanism, for instance, by traffic, you your solids are being suspended and end up being dust, or they're being washed off by the rain and so on. And many of these chemical deicers or anti-icers, they contain mostly chloride salts, and these are very corrosive to your vehicles, steel bridges, and reinforced concrete structures. And these ions are very mobile, very difficult to remove. So in the long run, it poses a significant risk to the society. And well, then you may ask, why do we even put salt on the road? Because winter weather is, a challenge to traffic mobility. Various case studies have reported during winter weather, we see reductions in free flow speed. We see reductions in traffic volume. We also see reductions in traffic capacity. So there is a need to do some winter road maintenance operations. Such operations are vital to economy and safety. So in addition to improving mobility, such operations basically lead to fewer accidents, reduce travel costs, and reduce fuel usage, reduce vehicle emissions, energy consumption, and so on, sustain the economic productivity, and continued emergency services. One interesting case study we did a number of years ago for Minnesota Department of Transportation was looking at their current practice over the last 3 to 4 seasons and see, what was the cost-benefit ratio, at the current practice, which are not necessarily the best practices, but we basically quantified the main benefit was coming from the avoided accidents and reduced congestion. So it's approximately $220 million per year. If we just divide that number into the benefits divided by the cost, the benefit cost ratio is greater than 6.2. So in other words, for every dollar invested in highway winter maintenance operations, you reap the benefit of at least $6.2. And then on top of that, there are some benefits we did not really quantify or monetize, such as the lower risk of highway closures. Now, looking at the risk side, however, the current practice basically putting down approximately 9 tons of salt for each lane mile per year. And we then look at the drinking water limit by the EPA or Environmental Protection Agency of US. Typically, chloride ion limitation is 250 milligram per liter. So that translates to salt, 379 milligram per liter. So I did some rough calculation. Seems like their current practice could each year contaminate up to 5 million gallons of groundwater. So if you multiply that number by 4 lanes and 50 years, remember the salts don't really go away. They just move from one place to another. So you're talking about, now 1,000 million gallons of groundwater at risk at this rate it's going. Another case study shows here, well, first of all, this chart looks back, 1940s. As you can see, the United States have gradually, I would say, become addicted to road salts. So over time, there's exponential increase of salt usage. Now we're looking at, close to 20 million tons per year. And this number is kind of old. In the last 20 years, actually further increased. Now, if we look at the implication on groundwater, here we're talking about sampling done by a case study looking at the rural rivers feeding Baltimore water supply reservoirs. And the chloride concentration increased 3 times since 1960. And it's going towards that 250 milligram per liter. Of course, we're not there yet, but given another 100 years, it's quite possible. So in other words, in wintertime, we're trying to drive fast and safe from point A to point B. The unintended consequence might be we're asking the DOT to provide really high level service, and then they have to put down some salt, and then that translates to our grandkids drinking salty water. So it's a social dilemma. Now, there are many practices done by the departments of transportation. For instance, anti-icing is putting typical liquid in advance of the snow event to prevent bonding of the snow ice to pavement. And then there's de-icing. When the bond is already there, trying to break the bond, usually use a solid material. And pre-wetting usually is adding the liquid to solid material, to mostly improve its longevity on the roadway. Because the dry material can be easily blown away by traffic. There's a case study, for instance, showed that on highways, the dry sand is only last a few seconds before it's blown away by traffic. So pre-wetting the abrasives can certainly reduce the need for applications, one study said, by 50%. Similarly, when we look at pre-wetting the solid salt, here are the benefits reported by agencies. Again, these are not through scientific studies, they're more through anecdotal evidence. So minimize bounce and scatter, increase longevity on road, therefore less need for frequent applications. And also they tend to speed up the ice melting and penetration, improve de-icing performance, because the solids need to turn into liquid before they can start melting the ice and penetrate the ice. Well, even though this is a very popular best practice, but it's kind of strange. There's no reliable data to determine, how much is the best, what's the optimum pre-wetting rate or product type. So this presents a need because we, as we mentioned, there are many implications in such practices. For instance, if we can use the best practice of pre-wetting to reduce the amount of salt introduced into the environment, we could be talking about implications in these many dimensions, mobility, safety, environmental, infrastructure preservation, equipment preservation, and also cost savings. So let's look at the Pacific Northwest, how things are going. But before we do that, we actually conducted a separate survey from another project to look at a national situation, and the green highlighted states are the responding agencies, typically highway departments. And this picture looks pretty much the same as 10, 15 years ago. Most people use solids such as rock salt and abrasives, and liquids are mainly three types, sodium, magnesium, and calcium. And a newer trend in the last 10 years is there's an emerging use of beet juice as an enhancer, basically blending it somewhat with the salt brine. And the beet juice is seemingly green and harmless, but it actually presents some water quality challenges for aquatic species. And also most of the agencies use a corrosion inhibitor, which further adds to the potential toxicity of such products. Now, typical range of pre-wetting rate, like how much liquid to the solid, is around 7 to 15 gallons per liquids per ton of solid. This is very similar to what's reported in literature, and as we know, this number depends on the particle size distribution of the solid salt. A newer trend is also agencies are trying to increase that number significantly. So because they want quick reaction, of this solid salt on the ice. So for trucks equipped with certain pumps, they can make a slurry kind of material, but that's not the focus of this study. So when we look at Pacific Northwest, again, situation is very similar. The most commonly used pre-wetting rate is 10 to 12 gallons per ton. And but there's 1/3 of them use more than 15 gallons per ton. So like I said, there's no systematic study on it. So that's why actually I should mention what I present here is already reported in the published paper by ISC Journal of Code Regions Engineering, if you want more details. Again, looking at Pacific Northwest, just the 4 states here, the situation is very similar to the national picture. And most agencies do use both salt and sand, and sometimes a blend of both. Again, you look at the same liquid materials being used, and the application rate, the pre-wetting rate was very similar, and the application rate of pre-wetted salt is a function of pavement temperature and snowfall intensity, typically 50 to 400 pounds per lane mile. And for sand, it's much higher, it's up to 800 pounds. So now, armed with that knowledge, let's design some lab tests. The need for such lab tests is because in the field, there's so many factors that could affect the pre-wetting, the performance of pre-wetted salt. So in order to isolate some of the factors, we conducted the experiments in the well-controlled lab experiment environments first. So the first question come to mind was whether or not the pre-wetting contributed to ice melting. And we used a salt which was used by Washington State Department of Transportation. And we focused on 2 pavement temperatures, 25 degrees and 15 degrees Fahrenheit, and 5 liquids. The first 3 are most common. And then the number 4 is a beet juice blend with salt brine. It's also very increasingly common by agencies. And then the 5th one is a more proprietary product or additive we developed and then blend with salt brine. So the good news is that yes, pre-wetting the salt generally improves ice melting capacity. The x-axis is the time and y-axis is ice melted, how many milliliters per gram of de-icer applied, I mean pre-wetted salt applied. So in general, the trend is desirable. So at this warmer pavement temperature, 25 degrees, and a relatively high application rate, which is higher than what we typically see on highways, because we found in the lab, if we go with the more realistic, say 250 pounds per lane mile, the amount of ice melt was so small, and the error would be, I mean, the variation would be too large. So we had to increase this application rate. And in this typical pre-wetting range, 8 to 16 gallons per ton, it seems to be beneficial. Now, what about the colder temperature? You know, if it's 15 degrees, we also see the same trend, especially in this case, we end up having to increase the application rate further. Otherwise, again, probably there's not enough ice melt to differentiate them. Now, what's interesting is also the pre-wetting doesn't always improve ice melting capacity. So we conduct some statistical analysis, especially in some cases where the pavement temperature is warm, 25 degrees, and the application rate is high, 2,000 pounds per lane mile. And then you see some of these negative numbers, basically when the smaller, I mean, than 0.05, that means they're significantly worse than the dry salt. So that's kind of interesting. But again, on the upside, when we look at 15 minutes instead of 60 minutes, we do see a lot of benefits. In other words, the pre-wetting increase the speed of ice melting. But you also see in the middle, you know, the warm temperature and the high application rate, there's no statistical significant benefit. Now, what about the, you know, in addition to ice melting capacity, another parameter, actually 2 other parameters we want to look at. The ultimate one, of course, is the friction coefficient, which translates to, you know, the stopping distance when the vehicles try to brake on the icy pavement. Another one is the bond strength of the ice to the pavement, because we want to reduce that bond so that it's easily broken by traffic or by plowing. So we try to simulate that in the lab. Again, there's a lot of details, but 2 things I want to point out. One is the application rate in this case was quite realistic, 250 pounds per lane mile, but we couldn't simulate the high-speed traffic. So we simulate very slow traffic, which may, you know, contribute to some variation we see later, and that also calls for some field operational tests. It's kind of interesting. This work was done at Montana State, where we grew our own snow. It was a drier snow with 30% moisture. So in other words, the results may be translated to areas with drier snow, but not areas like Minnesota, where the snow is a lot wetter. Now, the good news, again, is pre-wetting generally reduces the bond. But there are some exceptions where the bond was actually, bond strength was increased, which is highly undesirable. The best one we saw was the beet juice blend, where at a very small pre-wet rate, 8 gallons per ton, actually reduced the bond strength by half. So that's what we want. Now, to our surprise, the pre-wetting under the invested conditions actually generally decreased the pavement friction. So that's not what we want. Again, the good news is, again, for the beet juice blend at 8 gallons per ton, it did significantly increase the friction, but in many other cases, actually decrease the friction. So that's troubling. Maybe it's, the extra moisture we have introduced into the salt by pre-wetting the salt, or it could be because our application rate, pre-wet rate was still too low, because there was a case study in Ontario, Canada, talking about 44 gallons per ton. Well, this remains to be, answered. This is an open-ended question, but to summarize, pre-wetting is commonly performed by Pacific Northwest states. The state DOTs commonly at 10 to 12 gallons per ton, and typical application rate 50 to 400 pounds per lane mile. And for sand is up to 800 pounds. Now, it works well in terms of ice melting, especially when the temperature is warm and application rate is low. But when the permanent temperature is warm and application rate is too high, it actually has no significant benefit. And when we look at 5 products we tested, calcium chloride was the best one and mag chloride was the worst one. And so in lab tests, we see a lot of variation. And part of the reason we suspect is this fact we did not really simulate high-speed traffic. It was due to the limitation of the tests, and additional tests might be needed for statistical confidence. And again, a piece of good news is the beet juice blend worked really well at a low end of pre-wetting rate. So like I mentioned, there are certain key limitations of the lab test. We also didn't really quantify the benefits to reduce bounce and scatter because the traffic was so slow in the lab. So we need more field tests. This is only possible with the support of state agencies to conduct this on real highways, to see how pre-wetting reduce bounce and scatter, overall salt application rate, improve friction. Again, friction in the lab test was actually reduced. So that's pretty concerning, which might be true regardless of what people observe in the field, because they've never reported real numbers. Finally, I'd like to thank CAMMSE for supporting the work. This is more like exploratory work. Nobody has ever tested the pre-wetting effects. And my ex-colleague, Michelle Aiken, did a lot of work on this, and 2 students who assisted with the lab testing. Thank you, and I welcome your questions.
Thank you, Dr. Do you have any questions from the audience?
Also, feel free to email me, I guess. Like I said, the details are in that published ASC journal paper.
Very good. Thank you. That is very interesting research. Thank you for sharing with us. And now let's move on to the last speaker. Last speaker is Dr. Jin Zhu from University of Connecticut. And her topic will be entropy-based diversity qualification of multimodal transportation systems, physical infrastructure perspective versus travel behavior perspectives.
Thank you, Dr. Chi, for your introduction. Can you see my screen?
Yes.
Perfect. So hello, everyone. Good afternoon. My name is Jin Zhu. I'm assistant professor in Civil and Environmental Engineering Department at University of Connecticut. I joined UConn in 2017, and I'm kind of a pretty new member to CAMMSE. I got this very excited project last year, and I myself and my graduate student has worked on this project in the past year, and I'm very excited to report some phase result in today's presentation. So the title of my presentation today is Entropy-Based Diversity Quantification of Multimodal Transportation System using Physical Infrastructure Perspective versus Travel Behavior Perspective. So we all know that multimodal transportation system is very important for our future development, mainly for 2 reasons. First, car-dependent transportation has caused a lot of problems such as transportation congestion, air pollution, etc. Second, there is a large non-automobile travel demands. For example, we have seniors who cannot drive, and we have low-income households who cannot afford a car. So we need to consider these diverse travel demands and be more inclusive in our travel transportation system development. Despite applied all the study in a multimodal transportation system evaluation assessment, we find out a holistic approach to quantify the diversity of multimodal transportation system is still missing. So there are some studies who focus on the physical transportation infrastructure. For example, they look at the topological structure of different transportation infrastructure and assess their diversity level. However, these studies has failed to capture the human infrastructure interactions. In other words, they didn't pay attention to how humans are actually using this existing infrastructure. There are other studies who use like different surveys and focus group and try to ask people how satisfied you are with the transportation infrastructure or how you're traveling. So these studies usually rely on subjective rating system like this one we show here. So these studies capture the human behavior. However, they're kind of subjective in assessing the diversity of transportation users' behavior. So the research objective of this specific study of my presentation today is to develop an integrated framework to assess multimodal transportation system diversity, considering both transportation infrastructure and human travel behaviors. So we proposed such a framework. So in this framework, first we considered the diversity quantification from physical infrastructure perspective. So from physical infrastructure perspective, we capture the different level of service for different transportation modes, such as bus routes, like roadways, railways, work lanes and sidewalks and bike lanes, etc. And then we captured other important information such as the area size of each region we are assessing and the distribution of population in each region. And then we used these data to calculate the functional richness and functional evenness as two important indicators for diversity. And then we used a method called entropy weighted method to aggregate the functional richness and functional evenness for each area we're assessing, and then we can finally get a physical infrastructure diversity index to represent the diversity level of physical infrastructure in each region. And then on the right side, we look at the diversity of transportation system from the travel behavior perspective. So from the travel behavior perspective, what we get is based on the travel behavior survey, we calculate the number of trips made by each transportation mode in each region we're assessing. And then we use the entropy method, which is a widely used method to assess how diverse the different trips are made using different transportation mode to calculate the transportation travel behavior diversity in each region. And then finally, we can compare the physical infrastructure diversity value and the travel behavior diversity value in the same region and identify potential gaps between the existing infrastructure and travel needs in terms of diversity. So here are some details of how we did a calculation. For example, from physical infrastructure perspective, first we calculate the functional richness. The equation for functional richness basically is the level of service. So the level of service, depending on different transportation mode, we can calculate their level of service. If we are looking at the roadways, then it's calculated as the total length of the roadway network. If there's bus route we're looking, then we're looking at the length of the total bus route, and then we divide it by the area size of each region we're assessing. So we can calculate richness. Basically, richness is representing the abundance of the transportation mode in a region. And then we assess the functional evenness. You can look at the right. Here shows the equation and one example. So here the example we show is for the bus routes. So for the bus routes, what we did for the assessing region is first we find the centroids for all the centroids in this region. And then we assess the shortest distance from each centroid to the nearest bus station. And so we get a list of distance. So if all these distance, for example, they are same, means all the centroids in this region have the same, they have the same length distance to the shortest bus routes. So which means the service of bus service in this region is pretty homogeneous. So it's pretty even. However, if we are looking at all the distance, and some centroids have very long distance, some have really short distance, that means the distribution of the service in this region is really heterogeneous. In other words, it's not even. So that's how we calculate the evenness. And we use this method to we can calculate the richness and evenness for each transportation mode in each region. And then for the travel behavior, from the travel behavior perspective, what we did is we calculate using the travel behavior survey data. We calculate in each region the number of travel made using each mode. So here you can see this table just shows how we can organize this data, and then we can also calculate the percentage of the number of trips for each made using each mode that occupies the total number of trips made in each region we're looking at. And using this way, we can, using the entropy method to calculate travel behavior diversity. So the basic idea here is if in the same region, the number of trips you're making using each mode is same, then which means you're really having a really diverse distribution of travel using different mode. If in a region, you can see that most of the trips are made using, for example, car, then and there are very less or non-trips are made using walking mode or bicycling, then that basically shows that the travel behavior diversity in that region is pretty low. So this is a general idea how we assess the physical infrastructure diversity and travel behavior diversity. And this shows how we aggregated and get one single number for travel behavior diversity and physical infrastructure diversity. As I mentioned, we use the entropy weighted method to aggregate the richness and evenness value for each region, since we consider different transportation mode. And for each transportation mode, we'll have one richness value and one evenness value. And the idea of entropy weighted method is now we don't need to use subjective judgment to give weights for each value. Instead, the entropy weighted method will look at the values that have diversity, really diverse, or show like a big variation across different regions, and then automatically give more weights to those index. So and give less weights to index that show very similar trend across different regions. So this is entropy weighted method. And then in the right, we just use the entropy method to get the travel behavior diversity for each region. So we tested this method in a case study using the city of Hartford as a capital city of Connecticut. So why we choose Hartford? First, Hartford really has a commitment to facilitate the use of public transit service in the future. So that gives us some idea, like they are really looking at developing a multimodal transportation system. Second reason is that we see that Hartford has really a diverse socioeconomic backgrounds of residents in terms of income, age, gender, race. So this could give us potential more insights when we're looking at the infrastructure diversity and travel behavior diversity and want to understand why they show similar or different trends. So here we can see these are the data we used. So for, in terms of physical infrastructure diversity quantification. So here we can show the roadway network, bus routes, railway, bike routes, and sidewalks distribution in the Hartford area. So here, when the area we consider the units of analyze is zip code area. So City of Hartford has 6 zip code areas. So here, each zip code area is represented by one different colors in this figure. And we have laid out, put all these different transportation infrastructure in these 6 zip code areas. And we also consider ride sharing as the 6th transportation mode. So ride sharing, we used the City Ride as a website. This website provides the availability of ride sharing providers in different geographic locations. So based on this data, we can assess for each zip code area, what are the number of available ride-sharing service providers here. So this is the data we use to calculate physical infrastructure diversity. And this is the quantitative values we assessed. So here you can see that there are 6 zip code areas, and then for each zip code area, we calculated one richness value and one evenness value. And all the values shown here are already normalized value. And then for this case study, we quantified the travel behavior diversity. So the travel behavior diversity is quantified based on the statewide travel behavior survey for Connecticut conducted in 2017. So we considered the participate in the city of Hartford. In total, there are 2,631 household responses collected in Hartford area. And what they did in this survey is they reach out to this household, and if the household agreed to participate in the survey, they will provide all their travel behaviors in terms of when they made a trip, how they made a trip, how long the trip takes, etc. within 24 hours. So we aggregate this, we organize this data again by zip code area. Here you can see that for each zip code area, we know in this survey how many trips have been made through driving, how many trips were made through bus system, how many trips were made through cycling, walking, and ride sharing. So based on this raw data, we calculate using entropy method, we calculate diversity value in terms of travel behavior in each zip code area. So the last column here showed is the normalized diversity value in each zip code area. So aggregating the travel behavior diversity and physical infrastructure diversity, here we can see that the distribution of the diversity value using these two methods in these 6 zip code areas. So here in each figure, the darker the color is, the more diverse the value is. So basically we see that 06103 area has the highest diversity in terms of both physical infrastructure and travel behavior, and in Hartford regions, and for other zip code areas, we can see their specific numerical value here. So observing the data we get, we have several interesting findings. First is that travel behavior diversity is highly correlated with physical infrastructure diversity. In other words, they're not showing really different trend. They're showing, in terms of ranking, they're showing really similar trend. For example, we see that 06103 zip code area has the highest physical infrastructure diversity and travel behavior diversity, and 06105 zip code area has the second highest physical infrastructure diversity and also travel behavior diversity. And we can see that 06114 area has the lowest diversity value, both in terms of physical infrastructure and travel behavior. So this tells us what? It tells us since they are really closely correlated, if we want to improve the travel behavior diversity, then make an improvement in your physical infrastructure diversity could really help, because if you build more diverse physical infrastructure, then people really have the option to travel more diversely. The second observation we made through the result is people are resourceful in using diverse transportation modes. What does this mean? We can see that in terms of the figure on the top is physical infrastructure diversity. We can see that they are really show a big variation. For example, 06103 area shows a diversity value of 1, and all other zip code areas has a big difference between their physical infrastructure diversity value and 06103 area, right? However, if we look at the figure below about travel behavior diversity, the variability across different zip code areas is not that significant. So the highest one is 06103. They have a diverse value of 1, and the lowest still have a travel behavior diversity of around 0.7. So it means even if your infrastructure diversity condition is not ideal, people can still be resourceful in utilizing this existing transportation infrastructure they have. So this tells us what? It tells us if we want to improve the travel behavior of the system, besides improving the transportation infrastructure, making more investment to build more diverse infrastructure, we can also think more about the human perspective, like doing some making people more informed about the benefits of travel more diverse, and doing some, for example, social media campaign to change human behavior. The third observation we make is from the observation of these physical infrastructure diversity and travel behavior diversity across different zip code areas, we see there are some zip code areas show kind of abnormal behavior. For example, here for for these 4 zip code area, we can see that 06106, 06112, 06114, and 06120, their physical infrastructure diversity is pretty similar. However, if we look at the travel behavior diversity, 06112, this zip code area shows a pretty high travel behavior diversity. And we were wondering why. And one direction we explored is we want to look at the different socioeconomic factors across different zip code areas and try to see whether different socioeconomic factors could help explain the gaps between the infrastructure and travel behavior diversity. And specifically, we look at these 4 zip code areas, and specifically, we want to know why 06112 zip code area shows some abnormal behavior. And we actually find some interesting findings. So the first findings we find out is we look at the population distribution in terms of gender across these 4 zip code areas. And it's very obvious in 06112, sorry. In this zip code area, the female population actually occupies a larger percentage compared with the other 3 zip code areas. And this may contribute to the fact that 06112, in this zip code area, people travel more diversely, because studies have found that women are more likely to choose low carbon transportation modes such as public transit, walking, and cycling than men due to the nature of their trips. They usually make shorter travel distance due to the purpose of their travel. The second observation we made is we look at the age distribution across these 4 zip code areas. And what we find about 06112, the unique factor of 06112, is they have a larger percentage of population in the age group of 15 to 24. So you can see that all 3 other zip code areas has the less than 20% in this age group, while in 06112, there are 21.6% of the age population in this age group. And this again may contribute to the fact that people in this zip code area are travel more diverse, although they have similar infrastructure condition compared with the other 3 zip code areas, because young workers in this age group are more likely to choose non-motorized commuting compared with older counterparts, mainly because their physical ability and income level. So this is again some historic existing study has informed us this trend. And the last observation we made in terms of socioeconomic factor is the in terms of race. So what do we find out about 06112? The difference between this zip code area and other zip code area is they have a really high percentage of Hispanic, Asian, and Black population. Especially we can see that in this zip code area, the Black population occupies 77.3%, which is pretty high. And according to existing study, we know that white residents are more tend to use cars as their main transportation modes, since they are more likely to drive along and work from home. However, Hispanic, Asian, and Black residents tend to use more diverse transportation mode, such as carpool, public transit, cycling, etc. So this again is one potential contributing factors to our observation that why this zip code area show like a different ranking in terms of their travel behavior diversity and physical infrastructure diversity. So as conclusion, here are some contributions we think the existing study we conducted in the past year has made. First, we proposed an integrated framework to assess multimodal transportation system diversity from both infrastructure and human perspectives. And if we implement this to a more broader scope, there's a potential that we can create some quantification systems that in the future we can assess whether a specific diversity goal of a multimodal transportation system is achieved or not. And from our observations, such as the socioeconomic factors, there's potential we can identify a list of actions to promote transportation system diversity. So as I mentioned, it's an ongoing project. So in the future, we want to use this methodology, but test it in more zip code areas. So basically, we want to build some database and do more comparative analysis about this travel behavior diversity and physical infrastructure diversity. And we plan to incorporate more socioeconomic factors into our consideration. And another direction we're thinking to expand the study is to link the level of diversity of the transportation system with some travel behaviors, especially in the face of extreme events. For example, would the diversity value of a specific region affect the evacuation behaviors of residents in a specific region? So with this, I conclude my presentation and I'm open to questions.
Very good. Any questions from our audience? Okay, very interesting research. I have one small question, maybe a comment. Because you talk about diversity, child behavior diversity, weather may also play some role in this diversity. Because we always talk about in Houston area, where we not cycling or we not work a lot because it's too hot. Okay, so this may be one of the factors you can consider in your future research if you export your research to more wide area. In different region, you may think about the weather that also affect.
Yeah, sure. That's a really good comment. I said, like, if we want to expand it to other regions, we can actually incorporate more factors and do some more root cause analysis to identify why people are doing this and what's the difference in terms of physical infrastructure and other variety of factors. Thank you.
You're welcome. Thank you. Very interesting research. Okay, so this is the end of this session. I think we have some really good presentations. So now I think our director, Dr. Fan, will give us some end of the day remark. Dr. Fan.
Okay, thank you, Dr. Yi. Can everybody hear me, right? Okay, thank you. So what a day. We had a lot of great presentations today, didn't we? I really learned a lot and had a great time. I hope you are too. Okay, as we talked about early this morning, CAMMSE will address the FAST Act research priority areas of improving mobility of people and goods by focusing on developing advanced technology, methods, and models for multimodal transportation, including highway, public transit, bicycle, and pedestrian, as well as educating and developing an effective workforce. As you know, CAMMSE's vision is this, a collaborative research, education, and outreach partnership. We harness advanced computing, smartphones, and communication technologies, and ubiquitous data for creating sustainable, efficient, and growth-enabling multimodal transportation system using cutting-edge analytics models and methods. Again, as you've heard, we have a lot of great presentation today. For example, early in the morning, the first session, we have Dr. Randy Mockmail, Dr. Mehdi Azimi, Dr. Carol Atkins Palumbo, and Dr. Yi Qi talking about emerging mobility service, technology, and operations. And then the second presentation, we had Dr. Stephen Boyce, myself, Dr. Nick Lowndes, and Dr. Claudio Kirsten talking about research in the area of connected and autonomous vehicle and machine learning applications. And then we have a great student lightning talk session, as well as our third technical session, which focused on improving multimodal mobility, leveraging data and advanced analytics. Dr. John Avan, Dr. Jeff Cohen, and Xianming Shi and Jin Zhu made a great presentations. As you can see, all these research presentations align well with CAMMSE's vision. I would like to sincerely thank you for your time and hard work. Thank you for sharing the results and findings of your research with our CAMMSE family members and the broader CATC community. Tomorrow, we will have 2 workshops entitled "Are E-Scooters a Transit Last Mile Solutions?" To be delivered by Dr. Randy Mockmail from the University of Texas at Austin. And the second workshop entitled signal timing and geometry design at intersections with contraflow left turn lanes by Dr. Yi Qi from Texas Southern University. Again, all sessions and workshops will offer professional development hours. And please do not forget that we will start 9 o'clock Eastern time in the morning, okay? So with that, I would like to conclude our first day of the CAMMSE Research Symposium. I hope you have had a great day, great time, and enjoy your evening. Thanks again to all the presenters and participants. Stay safe, and I will see you tomorrow. Thank you.
Thank you.
Thanks.